Alright, physics students, welcome. This is an instructional on pendulum freefall, and today and tomorrow you're going to be working on the paper using the Google Chromebooks or laptops, whichever are selected for our room tomorrow. And if you go to my website, you will be able to find a copy of both this sheet of paper right here that says pendulum freefall instructions, and you'll be able to find this, which is actually on the same document. It's sort of a general grid to help you figure out what you're supposed to do. And then you're also going to find the rubric, which will kind of tell you what it is that you need to do. So for the paper, what you need to do, you need to be able to describe the forces, motion, and energy of the pendulum freefall experiment. And again, just to refresh your memory, that experiment is where we have two posts coming up out of the table like so, and you're going to have a weight attached to two strings, which are then attached to posts that are coming out at you. And you're going to burn one string, and the weight is then going to fall like a pendulum, and once it reaches its lowest point, a razor blade is going to cut that string, and then the weight will go into free fall until it hits the ground. Ultimately, what you want to be able to do is to put a target down on the ground right here, and in order to do that you need to know what the displacement is right here, delta x. So here's how you need to do this. Let's take a look at the grid that I have for you here. Like I said, there are three main phases to the pendulum freefall. You have equilibrium, which is the part where it's just hanging by two strings, it's not moving or doing anything. You have the pendulum, this part right here, and then you have free fall. So I'll just label those up here. Now for each stage or each phase, you need to have a description of the forces, and really that's these first two boxes up here. So you want to do free body diagrams for the equilibrium phase, the pendulum phase, and the free fall phase right here. And again, you need to have the primary forces and the component forces, so X and Y, for all of these. If they exist, there may not be component forces for all the parts, but if they are needed, if you have a force that is not in the X or Y direction, then you're going to have to break that force up into X and Y components. From those diagrams, you're then going to do your Newton's second law equations. So sigma fx and sigma fy right here. And again, these are derived from the diagrams that you made up here. So you need to put in what the forces are, if you need to add or subtract them, and then you need to say what they're equal to. Are they equal to 0 if it's at rest, or are they equal to ma if it is accelerating? And you have to do those equations again for all three phases. The third part is energy. And let's see if we can focus in a little closer here. Alright, now on this grid I use some different notation, but K1 really, that's kinetic energy, so we've got, I'll just change that to KE1. I've got KE2. Then I've got U1 and U2. U1, U is just a different notation for potential energy. So we'll go potential energy 1, potential energy 2, and the same applies through the rest of the phases. Alright, so with the kinetic energy and potential energy, you want to say what is the kinetic energy during the equilibrium phase, during the pendulum phase, and during the free fall phase. Alright, so during the equilibrium phase, that should be pretty easy because there is no kinetic energy. So you know that these two are going to be equal. The other thing I would mention is that, you know, I have KE1 here and KE2, meaning that there's like a before and an after. Well, there really is no event when the weight is in equilibrium because it's not moving at all. So whatever it starts with, you know, say you shut your eyes for 10 seconds and you open your eyes again, it's exactly the same. So whatever KE1 and whatever KE1 is, KE2 is the same thing. PE1 and PE2 are going to be the same as well. That's not the case for the pendulum or for the free fall, because with the pendulum, if you take a look at this, it starts out at one energy and it ends at another. And the same is true for free fall. It starts out with some potential energy and it ends with another down here. So let's go back to this. What we find is that whatever your finishing energy is, kinetic or potential, in one phase, that is the starting energy in the next phase. And the same is going to be true over here. With equilibrium, again, there is no change in kinetic energy or potential energy. And probably the most common question I get is, well, what do we put in for the numbers? For this project, you will not be putting any numbers in until Monday when you actually perform the lab. You need to figure out what your equation is going to be without numbers. So all you're going to have are equations and algebraic expressions, but you can use labels. And I think an important label to use here is to label the heights. And I think I have this on the board too at school, but when it's in equilibrium, you can call that height off the ground H1. At the lowest point of the pendulum, you're going to call that H2, and then the ground where it hits is H3 or 0. 0 is a number that you can actually use. So when you're figuring out, well, what's the potential energy of the weight when it's in equilibrium, well, what's our equation for potential energy? It's PE equals mgh. And which h are we using for this one? We're using H1. So then when you get to the pendulum phase, you're starting with a potential energy of mgh1, and then you're going down here to H2. So what would the potential energy there be? That's what you would put in for the next potential energy here. Now we know that equilibrium starts out with 0 kinetic energy, but we also know that at the bottom of a pendulum swing, that's where it's going the fastest. So there is a velocity here, there is a non-zero kinetic energy. So the question is, where did that kinetic energy come from? It came from the loss of potential energy here. So how much potential energy did we lose? Well, we started out with mgh1, now we're down to mgh2. So the difference between those two is equal to your kinetic energy. 0, the original, plus the change or the loss of potential energy. So on your grid sheet here, you would place, you know you're starting with 0, then this is going to be the difference between these two energies. But it's also equal to 1/2 mv squared. Okay, so you want to say 1/2 mv squared is equal to the difference between these two. And you want all of that written down. Because the reason is, you are going to want to know what this velocity is. This velocity is very important because we know that it's a horizontal velocity. We know that velocity never changes all the way down. And so if we know how long or how much time it takes for this to fall, and we know a velocity, we have what delta x is going to be. So let's keep that in mind. The last thing I would mention is when you move into the free fall phase, you know the same thing is going to happen. You're going to go from mgh2 down to 0. So you're going to lose mgh2 joules of potential energy. And you're going to gain that much kinetic energy. So right here on the chart, you've got 1/2 mv squared equals the change in potential energy here. But now you're going to add the change in potential energy here to that for kinetic energy 6. That's the final kinetic energy. And you want to look at that kinetic energy and see how it compares to the initial potential energy. If you know the law of conservation of energy, that should be somewhat clear. All right. Now, again, back to our original goal here, that is to find delta x. Where are we going to put our target for when we actually perform this lab? Like I said, you want to know what v is right here. And you're going to figure that out, but for each phase you want to be able to describe the motion as well. So in the motion boxes down here, you want to do your variable tables. So vx, v naught x, ax, delta x, t, vy, v naught y, ay, delta y, and t. And you want to fill these in. Now for equilibrium, that's going to be pretty easy because it's not moving at all. They're all zeros. But for the next two boxes, they're not as easy. And for this box, you know, there are going to be some things that you can fill in. There are going to be some things you can't. I would recommend that for accelerations, take a look at your force equations up here, and you can solve for A. Again, you're not going to get any numbers. You're just going to get some algebraic expression. So you can fill that in down here. But your Vx, again, it's this Vx right here, this final velocity, you will get from your conservation of energy equation that you have here, solving for V. That Vx is the V naught x in the last phase. So in the last phase, you want that V naught x. You also know that you're going to have to find the time, and I'll just give you a hint. Time will come from the y variables. And you're going to have enough stuff in y to be able to solve for time. Again, you're not going to get a number, you're going to have an algebraic expression. So you will have an algebraic expression for V naught x, you're going to have an algebraic expression for t, and you can multiply those together in order to find delta x. Again, using our equations of motion, which include v equals v naught plus at, delta x equals 1/2 v plus v naught times t, delta x equals v naught t plus 1/2 at squared, and v squared equals v naught squared plus 2a delta x. Alright, now obviously you want something with time in it, so it's not going to be that last one. But think about when we did our zero launch angle problem, or when we did the ball rolling off the table lab, we knew how to figure out this problem, where to put the cup in order to catch the ball. So use a y equation, look at your y variables that you have written down here. Just one more hint, ay is equal to negative g. You're not going to put 9.8 in. Again, no numbers, just letters. So negative g will be your ay. And that information will be useful to you in order to solve for t. Again, your delta y in that case, you're going from h2 down to h3 or 0. So 0 minus h2 would be your delta y. Okay, so that's kind of where you're going with all of this. Now, in the actual paper, I don't want you to copy this down and then just paste it into the paper. What I want is like an actual paper that you write. So here are some ideas for that. Like any paper that you're going to write, I want an introduction. And again, this is basically just to explain what you're going to be doing. Right? You're going to do the pendulum free fall lab and say, you know, it involves these posts, a weight that's going to swing, and you're going to predict where it lands. And in doing so, you're going to be describing the forces, motion, and energy of each phase of the situation. So explain what you're going to be doing. I would recommend a diagram of the setup. All right, and those are not free body diagrams. It's just a diagram kind of like this one here. All right, then you've got 3 paragraphs really that you need to write about. You need to write about the forces, the motion, and the energy, and you need to do that for each phase. So forces in equilibrium, pendulum, and free fall. And you would do that for each of these. That's one option. The other option is you can talk about equilibrium, pendulum, and free fall, and then for each one of those talk about forces, motion, and energy, like a paragraph about that. Now, I think I mentioned this to you the other day, but when I was in college prep writing, our teacher always said when you're doing research or something like that, quotation, explanation. You want to have a quote, then you want to explain it. For this paper, it's not a quotation that we're looking for, but it's an equation or it's a drawing. So you want to include those free body diagrams, you want to include Newton's equations, and when you put those in, say, you know, we know, for example, in the equilibrium phase, you could say the weight is not moving, there are forces, but they're all balancing each other out. The forces in the y direction are, the y direction forces of the ropes are balancing out the force of gravity, so there is no motion, no acceleration in that direction. The x components of those ropes are opposite one another, so there is no acceleration in the x direction, therefore there is no motion. And at least no acceleration, but we know it's not moving because we can see that. And then you would do the same thing for pendulum and for free fall. All right. On the rubric sheet, you're going to see that there are 7 categories. We've got forces, motion, energy, predictions, measurements and predictions, lab setup, and error analysis. These first 4 boxes are what you're working on today, or Thursday and Friday. Forces, motion, energy are what I've talked about already. The prediction is that last equation for delta x. All right, and you can see what it takes to get a 0, 1, 2, 3, or 4 for each of these. These last 3 are going to be included once you start doing the lab on Monday. Now I've provided 3 days to do that lab. It does not take 3 days to do, but my guess is that you might still need some time to work on the paper on Monday. I would really like you to have it done by the end of the day, Friday though. So anyway, these will be measurements you make and predictions you make using this equation in the actual lab that you do. Those findings will then be put into the paper as well, and then the paper is due on Wednesday. I guess the last thing I would say regarding this is that when you do this paper, again, it has to be done on Google Docs. You have to share it with me and give me editing privileges so that I can see it and I can make comments on it and you can make corrections as you go. So that's about it. Peace. You like that?
Peace. You didn't say peace out? Do you say that at the end of class every day too?
No.
I think it'd be like, okay, Mr. Lynch.
No!
It didn't work?
I didn't record it.
Oh, Nathan.
Shoot. All right. How did I not? Oh, bummer. Okay. Well, let's try this again. I knew I was forgetting something. Oh, I did. Ha.